G'day folks, welcome back to the term. Sorry for the late start. I've had a couple of health issues, finally back on track now though. So I was sent a question asking me to explain some of the work in exercise 2H, which is on significant figures and scientific notation. Before I get into actual nuts and bolts of how to do some of the questions, just a couple of sort of points that I want to explain first. So why do we bother with significant figures? Well, because sometimes near enough is good enough. So for example, if I was to say to you that, I live 60 k's away from school, you think, okay, fair enough, Mr. Obeid lives 60 kilometres away from school. But if somebody was to come out and actually sort of like look it up on Google Maps or whatever, or get in their car and notice the odometer reading and drive out to my house from the school, and they had a look at the reading, and it said, 61 kilometres or 59 kilometres. Would anybody sit there and think, oh gosh, I can't believe that Obeid lied to me, He said 60 k's and I got in the car and it wasn't exactly 60 k's. What a liar. I just can't trust the guy. Would you think that, or would you think, he was rounding it off? Okay. Well, obviously I was rounding it off, right? So let's say that, you sat there and you thought, Mr. Obeid, not that I don't trust you, but really 60 kilometres? Well, actually it's 59 kilometres. You think, okay, fine, 59 kilometres. Mr. Obeid's being a little bit more accurate. What about if you came and you measured out and it was 59 kilometres and 170 metres? Would you sit there and say, oh look, I'm just devastated, Obeid lied to me? I asked him, I said, is it exactly 60 k's? And he said, no, it was 59. Well, then when I measured it, it was 59 kilometres and 170 metres, 130 metres or whatever it was. Would you think, oh look, I can't believe it, this guy can't be trusted, he's a liar? Or would you think, look, he's rounding off again? Okay. What's happening as we get more and more accurate with the way we describe exactly how far it is Mr. Obeid lives from Kooringal High School, what we're doing is we're looking at, we're making more and more digits in the actual distance I live significant. Okay. So if I basically look, the nearest 10 kilometres is fine, so I say 60 kilometres. And you think, well, no, then you say, well, I want to be more accurate. So, okay, fine, 59 kilometres. So now I've made a second digit significant. Okay, if it was 61 kilometres, I'd be making a second digit significant. Okay, and the more and more accuracy I get to, the more and more digits in the actual distance I am from school I'm making significant. Notice that I'm not changing the place value of any particular digit. So when I say 60 kilometres, or if I was to then be a bit more accurate and say 61 kilometres, well, that 6 there is in the tens column. That 6 there is in the tens column. I'm not changing the place value of anything, okay? Or even if it was like 59 kilometres, well, to the nearest 10 kilometres, that is in the same place value as that, okay? The place value doesn't change. So when we talk about significant figures, what we're doing is we're recognising the place value of the most significant figures, okay? And it carries over into scientific notation, but we're going to get there in a moment. So why do we have significant figures? Well, we speak in terms of significant figures because sometimes a certain degree of accuracy is enough. Okay, we don't need more than that little bit of accuracy. Okay, so that's why we speak about significant figures. Now, but it doesn't just work in terms of accuracy. It also, in terms of getting more and more accurate. I suppose it does. So it's not just more and more digits on this side making us that become significant. It's the same for really, really small numbers as well. So if I was to tell you that, I've got a new microscope. I'm not into like microscopes and stuff. But let's say I've got this new microscope, and it's great, you know, you can see things that are 0 centimetres long. And you think, well, something that's 0 centimetres long is not there. What do you mean you can see something that's 0 centimetres long? And I think, oh, well, you know, I mean 0.0. Well, you still can't see anything. Oh, sorry, I mean 0.001. Okay. Well, when we're making our digits smaller and smaller, well, these zeros we say are not significant. In the same way that in the 60 kilometres, when it was really 61 kilometres, I'm saying that 0 is not a significant digit. It doesn't count. Right? So zeros here, you know, sort of before we actually get to non-zero digits, are not significant either. So I'm starting to kind of sort of work down away from the y into some of the rules. So when we're talking about significant figures, we're talking about a really small, a really large number. So let's say I'm talking about the population of Australia, which is 27,475,325 people. And I just made that number up, okay? So if I came along to you and said, oh, look, what's the population of Australia? And you said, oh, 27 million. Okay, well, you're saying that if this is the way you describe the population of Australia, then you're saying that there are only 2 significant figures. You're saying that, look, I'm not worried about the accuracy below like 500,000 people, okay? So these zeros are not significant. Zeros at the end of a big number are not significant, okay? Same deal, zeros at the start of a small number are not significant. So if I was to say how many significant digits are there, or how many significant figures are there in this number, well, there's 1 significant digit, okay? And not because it's the numeral 1, it could be any numeral, right? This number here has 1 significant digit, okay? This number here has 2 significant digits, or 2 significant figures, okay? Those first 2, because I've basically just sort of like reduced everything else to a 0. So zeros at the end are not significant. Zeros at the start are not significant. Now you need to write them in, right? If I was to say, well, what's the population of Australia? You can't just come along and say, oh, it's 27. No, it's not. I mean, the population of our class is more than 27. Okay, when we're all here. But so it's important that we keep our place value. So the zeros belong there, but they're not significant figures. Only the non-zero digits are significant figures. So zeros at the end, not significant. Zeros at the start, not significant. Okay, so that leads us on to the question of rounding a number off to a given number of significant digits. Okay, so if I was to give you, say, well, let's go back to that you know, the number I made up for the population. 27,435,251. Again, I'm just making up the number. I know it's not the same number I had before. But let's say I said that was the population of Australia. Right? If I said I want you to round that number off to 2 significant figures, okay? What you do is you basically come along and you find the first significant figure. So the first significant figure is that 2. And then you count, I said I wanted 2 significant figures. So we count 1, 2, and then we draw a line, okay? And then we just round off with the normal rules we use for rounding off when we're doing decimals, the one you learned back in year 7. So we follow exactly the same rules, but we have to keep our place value. That's how this is a little bit different, okay? So let's do that. So, well, because that number is less than 5, well then when I round off, I don't take that up to an 8, it stays as a 27. But the 27's got to keep its place value. Well, that means that all these other numbers here become zeros. That's that number rounded off to 2 significant figures. What if I wanted 3 significant, or let's go to 4 significant figures. So if I want to round off 27,435,251 to 4 significant figures, okay? Well, I count 4 digits. 1, 2, 3, 4. And then I draw a line. and I round off exactly like I did with decimals, but I've got to keep place value in mind. Well, because this number is 5 or bigger, that number rounds up, but everything's got to keep its place value, so all these other digits become zeros. Okay, so 27,444,000 to 4 significant figures. Okay, same for really, really small numbers as well. So if I was to look at 0.0003751, if I wanted that number to 1 significant digit, well, I come along, I find the first significant digit. So all the zeros on the left, remember, are not significant. That's the first significant digit, that 3. I draw a line down and I round off like normal. Well, because that number is 5 or bigger, this number here rounds up, so it becomes a 4. Okay. Now, I don't bother putting in these zeros because I only put zeros in at the end to keep my place value. Okay. I don't need that place value anymore. Okay. So that number there is this number rounded off to 1 significant figure. Okay. If I wanted 2 significant figures, I do exactly the same thing. I go 1, 2, I draw my line and I follow the same rules for rounding off. Okay. So that's how we round off a number to a given number of significant figures. If we understand that, let's now look at scientific notation. Okay. So we often, and probably rightly so, we think about science as being all about accuracy and precision, and to some degree, some branches of science are like that. Other branches of science, we more care about sort of orders of magnitude. So in other words, is it hundreds of thousands or is it millions? Is it hundreds or is it thousands? Is it thousands or is it 10,000s? Is it hundredths or is it tenths, for example? So scientific notation is about generally the size of a number. What do I mean? In scientific notation, what we want to do is we want to be able to write a number so that there is 1 digit in front of the decimal point. And then everything else is basically expressed as a multiple or a power of 10. So think about this number here. Think about the number, 257,419. Okay, I was just deliberately sort of picking all the different digits in there. So if I want to write this number in scientific notation, well, at the moment, I'm just going to put a decimal point in. Actually, no, I won't. There's no decimal point. It's 257,419. Okay. If I want to write this number in scientific notation, well, that means that I need to have 1 number in front of the decimal point. Well, right now the decimal point's over here. Even if it's not written, I know that that's where the decimal point belongs. It's after the ones, the number in the ones column. Right? So that's where my decimal point is. I need to move it so that it's over there. Okay. Well, think about what this number is. Take yourself back, to primary school when you would have played with an abacus. Okay, you remember abacuses? They were those boards. I'm going to do a very bad drawing of right now. Okay, and you had like a wire that started on the front here and went over the top. Another wire that went over the top. Another wire that went over the top. And you had these different coloured beads. Now you're meant to make different numbers. You remember those toys, right? I mean, everybody had them, or they're in parks near where you grew up. So this number here's got 4 digits there, and 4 beans there rather, and 2 beans there, and 3 there. So that would be the number 324. Okay, that was in the ones column, the tens column, the hundreds column. Okay, so literally that wire represented hundreds, that wire represented tens, that wire represented ones. Well, what wire would this number represent? Well, that's ones, tens, hundreds, thousands, 10,000s, 100,000s. Okay, so that means that when I write this number here in scientific notation, well, that 2 still needs to represent hundreds of thousands. Okay, so the way we do that is to basically talk about the number of places we have moved our decimal point. So look at this, we move our decimal point 1, 2, 3, 4, 5 places to get it there. So we write this number as 2.57419 times 10 to the power of 5, because we moved our decimal point 5 places. Okay. Let me do one where we've got a really small number. Well, let me do one where we've got the decimal point in a different spot. So let's say we had the number, 427.65. Okay. Well, the decimal point needs to only have one digit in front of it. So it needs to move from here, 2 places to there. So this number is going to be 4.2765. We moved our decimal point 2 places. So it's times 10 to the power of 2. Right? So I count the number of places I had to move my decimal point. What about if I've got a small number? What if I've got 0.00473? Well, remember I want one non-zero digit in front of my decimal point. So that decimal point there has got to move so that it's in front of that 4 there. It's going to be 4.73. Well, this one's a small number. I'm not going to write 4.73 times 10 to the power of 3 because I jumped 1, 2, 3 places, because it's a small number to show that, so just like our abacus, we had the ones, tens, hundreds. Well, when we go past the decimal point, we've got tenths, hundredths, thousandths, tens of thousandths, hundreds of thousandths, etc. Okay, so I need to show those fractions here. So it's going to be times 10 to the negative 3, because I jumped 3 places. Okay, so whether it's a big number or a small number, I look at the number of places I'm jumping with my decimal point, and that's how I express my number. Now, if we're reversing this, if I was to give you this number and ask you to write it not in scientific notation, just in standard notation, well, that negative tells you that you're jumping the decimal point back to the left. Likewise, this positive power tells me you're jumping the decimal point to the right. Okay? So when you're writing in standard notation, take note, the power tells you which direction to jump your decimal point in. Okay, so how do we put these two things together? How do we put significant figures and scientific notation together? Well, it's really simple. If I've got, let me look at my first number up here. So if I've got this number here, 2.57419 times 10 to the 5, and somebody says, Mr. Obeid, how do I write this number to 3 significant figures or 2 significant figures? Well, I go 1, 2, 3, if we're doing 3 significant figures, and I round off with my normal rules, because that's not bigger than 5, I leave that alone. So I get 2.57 times 10 to the 5. And that's it, that's job done. Okay, so if I want to express a number that's in scientific notation to a number of significant figures, I just round it off like I normally would for significant figures. Just ignoring, I don't care where the decimal point is, I'm just going to follow my rules for significant figures. Okay, so look, I hope that's enough for you to make a start on exercise 2H. Don't sit there and say, well, look, I watched your video, I went to the hardest question and I couldn't do it. Make a start, work your way through. As you work through those easier problems, your skills will build up and you'll be surprised at your ability to handle some of the more challenging ones. Don't let that stop you from asking questions though. If there's anything at all you're not understanding, please shoot me a question via email, on Teams. If you're watching this on YouTube, then in the comments below. Okay, thanks very much, guys.